Our topic for this meeting is Alkyne. We are still under the main topic, hydrocarbon, and the alkynes here are shown in your screen is a carbon-to-carbon compound bonded together by triple bond. One, two, three, triple bond. Okay, let us try to compare the three hydrocarbons. First, we have discussed ethane or the single CC bond, ethene for the double CC bond, and ethyne for the triple CC bond. We have claimed that the carbon-to-carbon bond here is flexible since they follow also the angle of 1.54 and the carbon-to-hydrogen bond is 1.09. And then for carbon to carbon double bond 1.33. Here it had also decreased from 1.09 to 0.08. Sorry. And then we have 1.20 for triple CC bond and 1.06 for ethine. So in terms of energy requirement, the ethine or the triple bond needs more energy in order to break the CC bond. This is the electron cloud formula for your triple CC bond. So we have here your pi band. If you can remember your um, single band, you have a one pi structure, the one standing up, to represent the second band. Here you have the third band. So you have here the third band. The first band is the band represented by two lobes here. Then the second band is by the lobes formed in between. And then for the third lobe, you have this one. So that if you're going to draw, you could also draw it in a barrel type or in a cylinder type. And you could show here your hydrogen band with carbon. So it could also be illustrated in this manner or also in this manner. What are the uses of alkanes? Alkynes are usually met or the byproduct or where it is used are usually seen in our day-to-day life. Acetylene. Acetylene is used for welding. It is used as oxyacetylene torch. For the gentlemen, maybe they are very familiar with this. When acetylene is burned in sufficient oxygen, we can get a temperature of around 3000 degrees centigrade. So you can just simply see the hazard faced by the welders. They are working with fire, they are working with torch, and the fire in the torch could yield 3000 degrees centigrade. High enough to melt metal parts and join them together while they are still in the soft condition. We have also chlorinated acetylene. It is a solvent. Similarly, acetylene is a starting material in the synthesis of polyvinyl chloride and also likewise polyacrylonitrile. This is an example of the PVC or polyvinyl chloride, the plastic tube that you could see outside the house in which that tube is used uh, for the rainwater runoff passes through during rainy season. It is also the same black pipe that is used in irrigating plants in the farm. And then you have here an example of a material made up of polyacrylonitrile. And I am sure you are familiar with this. This could also be used in the bathroom, or these are also used in the hospital as bed mat for patient. And then you have also alkyl carbanions and are very good nucleophiles and can be used to attack carbonyl compounds. Alkyl halides to give additional product, and thus they are important material in chain expansion of organic compound. This is more of a chemical function of alkyne. You are familiar with this. This is your acetylene tank, the tank in which welders get energy for their blue torch. This is full of acetylene. So if you have seen this structure or this thing as signage in this kinds of tank, that carbon there is bonded with three double bonds, three triple bonds, sorry. Now let's go to your most favorite activity in hydrocarbons, the IUPAC naming. The same principle, you look for the longest carbon chain in which the triple bond could be passed through. So in this case, you have this start here because you could already see that the carbon 1 is found in the first carbon. So carbon 1, carbon 2, 3, 4, 5, and then you have double bond here, 6, 7, an alkyl group, and a double bond, 8, 9, 10. That's 10, right? Okay. We could not just simply say here 7, 8, 9 because there is a longer chain here. You have 7, 8, 9, 10. So it is a deca. But since you have here a triple bond, you have the ine. Where is the triple bond? It is in the first carbon. What is the longest chain? It is uh, made up of 10. But there is a twist here. You have also double bond. So you write if there is a triple bond ine, where is the triple bond first carbon? There is also a double bond. Do not write in, but rather just simply en. And then since there are two, you write di. And where are these two double bonds? From the from from the longest carbon chain, they are in the 7 and 8. So you can still remember this, no? The E and the C. So you have the 5, 7 decadiene. And then you write the alkyl group. You have 1, 2 methyl. So dimethyl, you write there dimethyl. And they are found in carbon 7 and 8. So the name of this structure is 7,8 dimethyl 5,7 decadi in 1-ine. Or it could just simply be read as 7,8 dimethyl 5,7 decadi in ine. Never mind the 1. So you have here other examples, both aliphatic and aromatic example. So you have here a triple bond, so you write there ine. There are 1, 2, 3, 4, 5 penta, so it is pentyne. The carbon 1 contains the triple bond, so this is pentyne or 1-pentyne. And then you have here a triple bond, so you write there ine. How many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So decane, so you have decane. Where is carbon containing the triple bond or facing the triple bond? 1, 2, 3, 4. So the fourth carbon is facing the triple bond, so you write there 4 decyne. Okay, is the longest chain the triple bond or the double bond? There are only 1, 2, 3, 4. So the triple bond is just simply an alkyl, and then the cycle structure here contains double bond is the longer bond. So you have there it is containing 8 carbons. It is aromatic, so you write there cyclohexene. But since there is a double bond, you locate where is that triple bond, where is that carbon containing the double bond. So it is 1. Then you have also here the alkyl group. It contains 1, 2, 3, 4, and the triple bond is found in the second carbon. So it is 4-butynyl. So this is an alkene, although you have an alkyl with triple bond. Okay, this is 8. Benzene has always 8. 1, 2, 3, 4, 5, 6, 7, 8. You have here the ring. So the double bond could be here, here, and here. Or it could be expressed as the double bond could also be alternately placed here, here, and also there. So the double bond is placed alternately between the 6 carbons. So there are 6 carbons. I do not know the exact tail here. So maybe let us assume that if it is in 5-penyl, meaning to say the carbon is found in the fifth. So this is 1, this is 5, 4, 3, 2, 1. Then let's discuss the isomerisms in alkyne. So in terms of chain isomerisms, the triple bond could be just simply transferred to the other bonds, carbon to carbon bonds. So that is the positioning in terms of isomers, chain isomers. Then we have also functional group isomers. The compounds having same formula, but they are called functional group isomers because they are part of a bigger group of alkane. So the triple bond could be part of a cyclopentene or could even be a part of a larger aliphatic compound, thus serving this only as an alkyl group or a functional group. Then you have also geometrical isomers in which they contain the same number of carbons, but these carbons are positioned as either alkyl group or even a cycloalkyl group. Then these are the properties of alkynes. Alkynes are colorless gases with a specific odor They are insoluble in water, but they are soluble in organic solvents like benzene and carbon tetrachloride. Performing experiment in the lab with alkyne um, requires you to have a healthy respiratory system because this experiment makes the laboratory room uh, produce several kinds of odor. So some are painful to the nose, some are painful to the chest. In fact, if my students perform this experiment in the lab, I allow them to go out of the room to breathe, or I allow them also to I require them to open the windows for proper ventilation. There are some instances that some of the experiments are also performed in the fume hood. Okay. The first four members of the alkyne are colorless gases, whereas the next 5 to 6 members are liquid. The bronze alkynes have low boiling points. The linear alkynes, due to due, uh, due to compact packing efficiency, as compared with the aromatic one. Where am I now? Number 3. The hydrocarbon ratio, at least in alkynes, and hence they burn with salty flame due to incomplete combustion. Since there are so many bonds to break, more energy is needed. But the combustion of alkynes produces a lot of smoke, odorful smoke. The alkynes having triple bond in the last carbon atom are called terminal alkynes, just as the same with other hydrocarbons. The terminal alkynes are polarized due to electronegative nature of the carbon. That is also true with alkenes and alkynes. Okay, in terms of acidity, let us start to compare alkynes with the others. So these are the hydrocarbons working with the base. So in terms of hybridization, you have this. So as you go down, the more double bond, the lower is the acidity or the pH. So this is more acidic as compared to this, and this is more acidic as compared to this. In front of you is the enzyme anti-tumor agent reaction. This portion here. Get my pointer. This structure here refers to your NDI, anti-tumor agent. I would like you to have the mind setting that the only one that will be reacting here is this structure containing the triple bond. This structure containing your OH and your benzene ring will never be affected by this reaction. Now you focus your eyes into this structure alone and how this thing is changing in the reaction. So if we're going to look at this carbon, it has a double bond and also a single bond at the bottom. Here you have the double bond and the single bond at the bottom, right? So the next carbon here, up to there is single bond. The next carbon here is the same, single CC bond. But there was already a change after cycloaromatization between the triple bonds, both in the triple bonds. The one of the bonds of the triple bond had made itself free for reaction. So this become one dot and that also became one dot. This is also one dot and one electron dot. So one electron dot had bonded together. So this one. And one electron dot merged out and one electron dot also merged out, leaving double bond and double bond here. Okay. So after that, after that, the two electrons have also bonded together. So there is now this line that is supposed to be placed here. So the series of the going out of electron had formed the double bond here and the single bond. And then one electron went out. So this is now the one electron. And this is also the other electron. Okay? Can you get that? This portion here and this portion here is actually this one and this one. It was only tilted in a manner like that. This is also tilted in a manner like that. So these three carbons here are the same as the three carbons there. So what did cycloaromatization done to here is the formation of the bond here. The formation of the bond here. But making or leaving one electron each. So in complete abstraction, those electrons reacted with other compound, making or leaving this structure. Is that clear? So nothing happened to the other functional group. What only happened is the changing of the triple bond to form dicyclo compound. Okay, this is dineomycin A. It is also an anti-tumor. So you have here the blue color containing the triple bond. All the rest, wala siyang triple bond. So the main actor here is this aromatic structure containing the triple bond. What happened is this. So this is, of course, some things will be also affected here, some things will also be affected here. But however, most of the things that will be affected are those directly attached to the one with triple bond. So cycloaromatization, this will happen. So this is the thing that will be free. Okay. So this structure contains also a structure that will not be involved except for the carbon to carbon here. And then this structure, what will be affected will be the one that are directly in contact with oxygen to oxygen. So, from here, ito yun, triple bond. Ang mangyayari is, yung oxygen will be working with this 3. So, yung oxygen, nandito yon, oxygen, oxygen. So, there is no change. But the carbon containing oxygen bonded with one carbon, if you're going to look at, there is an attack here, no? This one had attacked this and had taken the hydrogen away. The leaving off of hydrogen makes this double bond, this one. But the double bond here, if you notice, the double bond here had formed a bond here. Okay, you have that. So I repeat, there is this connection here, right? So you have there the reference carbon, and here you have the double bond. Okay. The double bond carbon here is directly attached to the structure with triple bond. But what will happen is the triple bond will bring out one of its electron, and this one will also bring out one of its electron, thus having to close this one and also forming now this structure. So when this was formed, the penile ring here was formed. So this is the one that had changed. And the closure of that one cyclo structure had led to the opening of two adjacent cyclostructure. So when this cyclostructure was formed, the double bond here, ito, the double bond here had worked with this structure and worked until this portion, the double bond. And this became possible because of the removal of hydrogen. The removal of hydrogen allowed to make the double bond, and then that double bond had made this single bond carbon to be attached now with another bond. So you have here the single bond, and one of the electron had left already, and then this portion here also uh, became closed, and then forming, eto yun, forming a bond here. So you have 1, 2, 3, 4, 5, 6. This is now your 1, 2, 3, 4, 5, 6. So this bond had also created a cyclo compound here. 1, 2, 3, 4, 5. So eto yun. So eto rin yun. Now the formation of this compound has also made the oxygen bond here to be freed with the presence of hydrogen. So the movement of the OH here freed the oxygen here, but made this double bond has allowed a single bond to be placed there, and then the closure of this one cyclo compound here and the formation of another uh, cyclo structure allow the oxygen to be freed with one bond, and then the other bond will be working with the hydrogen. So only this portion was affected in the reaction. So this one going there was affected. Okay, in terms of more uh, detailed explanation, ito yung nangyayari. So kung bakit nawala si hydrogen is because merong base. So if you notice kanina, I tried to go back because the reaction will lead to the leaving off of one bond in order for the oxygen to get the new bond. And there it is. These are just detailed illustration on what had happened. Then another reaction is the catalytic hydrogenation. So hydrogenation meaning to say there is an addition of hydrogen. So the addition of hydrogen will make a triple bond, double bond, and then an addition of hydrogen again to the double bond will make it single bond. So this is just a series. So in this case, if this is the example, you have there the triple CC bond. The addition of hydrogen will remove the first bond, and then further addition will remove of uh, one hydrogen bond, thus leaving also one carbon-to-carbon bond. So ang magiging product, if you're going to look at the picture behind me, you have already only one single bond. Okay, this is the Lindlar's reaction. In Lindlar's reaction, it is not the hydrogen that is affected, but one of the aromatic. Okay, we have also here another chemical reaction, hydrogen on Poisson catalyst. So we have here the triple bond in this structure, the 5-decyne. So if we say Poisson catalyst, we need the hydrogen, and the Poisson catalyst here is uh, the presence of quinoline or a Lindlar's catalyst. So what will happen? This triple bond with the action of quinoline or Lindlar's catalyst will produce first a double bond. But the production of double bond makes this transdecyne into cis decene. And the ultimate product is actually removing that double bond to make it single bond. So at my back is actually a decene. So your objective here is to remove the triple bond using quinoline or Lindlar's catalyst. And then you have also dissolved lithium in ammonia. So here is your triple bond. The addition of lithium in ammonia will first lead to double CC bond, and then this will result to the removal of some electrons here, resulting also to a single CC bond. So you could have the long process that is showing to you how the electrons here were removed. So one electron will go there, then the other electrons will go here, playing with ammonia, and then the double CC bond will be attacked by lithium, thus making this as the product, and so forth and so on. And this carbon to carbon double bond will again be subjected with lithium in ammonia until the single bond will be produced. The same process, the lithium will attack one of the electrons in the double bond, and one of the carbons will be working with the ammonia out, leaving one uh, single bond. So you have also addition of halide. In this case, you made use of HBr. So here is your triple bond, and then this is your double bond. So bale, ito natanggal, si Br pumasok, right? And then the other electron will be taken away by the H, and the Br will be going there. So the same again that will happen. The HBr will be working with one of the carbons containing the double bond, so making the bromine attached to the same carbon. So the product is this one. So you have the carbon here that is the same here, and the new bromine and the new bromine attached to it. Okay, you have also um, halogen addition. Last time it is acidic, the acid halogen, HBr. Here it is Br2. In the former example, you could also have HCl or HI. But in the bromine addition, it is both Br2. So this will not be involved because it does not have triple bond. So this is the one that you're going to look into only. So as a shortcut, you make the single bond, and for the first reaction, you have Br and you have Br, making it double bond. Now this double bond, you add again Br2, one of the double, here. The double bond will become single bond if this one bond will be attacked by one Br, and one carbon will be attacked also by one Br. So you have here the Br, the Br here, and the Br here. Of course, the hydrogen will always be there. So remove one bond, place bromine, and place the other bromine here to have the Br2 distribution. Continue. You have led to the formation of double bond. You remove the one bond by addition of Br again. So you place one Br to one carbon and one bromine to another carbon. So you have here already. Oxymercuration. Oxymercuration, it is the addition of mercuric sulfate, sulfuric acid. So what will happen first is the formation of enol. So uh, breaking this first to make it a double bond. So you have to gain one hydrogen to have the CH2, and you have to gain oxygen and hydrogen to form the OH here, form the enol group. And again, another oxygen for this one to make a double bond oxygen. Okay, then continue until you will have the single bond. And then you have the enol keto tautomeration. Just like in other tautomeration, your only objective here is to make a double bond O. Okay, so you remove the single bond from the double CC bond in order to produce a double CO bond. So if this is the original, you have OH there, but ang ginawa mo lang is you have transferred one of the oxygen here. Ito yun. You have transferred one of the oxygen here to make it CH3, and the bond from the oxygen hydrogen bond will go down, and one of the bond here will go up here because one of the electron from here was given to the new hydrogen. That is your enol keto tautomeration. It is characterized by the changing of the OH from the double CC band into double band CO. And then oxymercuration mechanism, what do you think is the product? That is the tautomeration process. It is the removal of one of the bond from the CC band to produce the double bond. There is a double bond and the addition hydrogen in the other band. You can have this to there to there. This is the specific explanation to it. When I was still a student, pag may exam kami, ito yung dapat mong ipalabas in order to come out with that. This is just simply a shortcut, but it could also be illustrated in this manner because this shows the process of enol formation. And then you have the hydration using the anti-Markovnikov's principle. So hydroboration, the addition of diacetylamylborane, peroxide, and hydrogen peroxide and sodium hydroxide is involved. The formula for diacetylamylborane is this one. Okay, what do you think is the product? Of course, you have to make this CC band to be attacked by this, allowing an enol first, and then you have the main product. So there is no more double bond, but rather a single bond. Hydroboration mechanism, acetylide formation. So how did this happen? Ito yung schematic diagram. But if we're going to put into reality, the R, here is this group. Okay, so this is the example. We have also alkylation of acetylide ion. So using S and 2 reaction, or homologations of using or homologous mechanism. So there is the breaking of the triple bond by the introduction of an amine here, thus the sodium plus and the NH negative working with this bond attached to the triple bond. This is carbon 1. So what will happen is the hydrogen will be leaving in order for the sodium here to take its place. So in this case, you have here the carbon attached already to the sodium. Okay. And thus you have here CH3, CH2, CH2, carbon, triple bond, carbon, CH3. So this is CH3, CH2, CH2. This is CH3, CH2, CH2. So this is the triple CC bond. This is the triple CC bond. What happened? The triple CC bond is now bonded with sodium. But with the addition of NH3, ito yun. Yun ha. Yung carbon became this one. Ito. Yung carbon na to became this one. So you have here the carbon single bond. Ultimately, the triple bond went to the second carbon or producing another CH3 here as an added carbon. So you have 1, 2, 3, 4, 5, 6. Originally, 1, 2, 3, 4, 5. Then you have 1, 2, 3, 4, 5. So upon working with NH2, the number of carbons is still the same. But the entry of sodium allowed alkylation, ito, removal of the bromine, alkylation to exit the alkyl group to be added, but the removal of an alkyl. So itong CH3 na to was added here. Okay? Nakuha nyo? Ito, nung una, natanggal, sodium. Pero nung pumasok si alkyl group na acetylide, ito, na sodium dati, naging CH3. Okay? So, bali ang nakipag-react is the first carbon. Nakuha niyo yun? So, bali, I repeat, si sodium, nakilaro dito, tinanggal niya si hydrogen. Pero eventually, ang nakipaglaro naman dito is an alkyl group containing an acetylene, an acetylide, may CH3. Nung upon addition of the CH3, syempre tumanggal si halide, kanya ito, eventually, napalitan ng CH3. So yung trono ni hydrogen naging sodium, pero eventually through alkylation of acetylide ions, si sodium natanggal din, napalitan ng CH3. So, eto from H to sodium to CH3. Okay? And then, this is also an illustration of nucleophilic addition of carbonyl compound. Madali lang to. So, bale, yung, ito yung triple bond. Ang gagawin lang dito is, papasok siya. Pero yung kanyang pagpasok, si C double bond O, naging single bond, and then eventually yung kanyang pagka-single bond dito, ito yon, nag-relasyon siya sa hydrogen. So, bale, ito ay magiging OH. Yan, nandyan pa rin yan. So, nucleophilic addition, si triple bond serve as a nucleus entering to the primary carbon containing the double bond, but making the double bond O into OH, single bond OH. That is your nucleophilic addition to the carbonyl group. So, you could have this as an exercise to determine what is the product. And then this is also another form of exercise. What if ozone is added? What will be the product here? Siyempre, again, be guided that the reaction should be focused only on triple bond. Okay, this is also another example to illustrate. However, I would like to tell you that there are some mechanisms in the alkyne that you could traverse back or go back. Okay, in your examination, pwede ang nakalagay lang is ito, triple bond na hydrocarbon. Tapos, itatanong kung ano ang product if these are added. Or what is the reaction involved pag ganito. In this case, example, what if CH3I is added? Ano ang mangyayari dito? Or what if this one is the one added? Ano mangyayari dito? Okay? So, ito will just simply guide you as to what will happen. Again, these are also some example of exam question. Complete the illustration. What if you have C11 is 14 and you are required to add this? What will be the product? What if from here you're going to add Grindlar's catalyst? Ano ang magiging product? So these are actually blank spaces that you're going to answer. Okay, these are just simply summary of what we have discussed. And then, again, these are things that you could use to understand some of the mechanisms that were presented earlier as a drill or a review.